match rates at the ADS scale, and no matter how big the black hole is, this is still the ADS time scale. There's actually a very good reason for that, also explained in our paper. And you can get it from the formulas, but we gave a nice reason for it related to the methods of singularity theorems, actually. Okay, so let's see, I think I better say this very quickly. Yeah, I just want to mention one thing really quickly. The idea of cutting off at the horizon, one thing we weren't worried about was, is this compatible with the switchback effect? One of the litmus tests of this idea of complexity equals volume or action was that it satisfied the property that the complexity satisfied the switchback effect, which I can't go into right now, but we checked that it does, provided to include the volume behind the white hole horizon, which actually we argued made sense because the white hole is a black hole backwards in time, and the switchback effect concerns looking at evolution that's partially backwards in time. But the full switchback effect account takes place just within the black and white hole horizons, and there's no need to consider anything outside. So let me just mention quickly, I guess, one other. I didn't manipulate this. Okay. One other thing I would say in our paper, among all the other fascinating results, is the idea of the volume flow or the gate current. So it turns out if you just give it a foliation of the boundary here, you get a foliation of the bulk by maximal volume slices. And orthogonal to each slice is a unit time-like vector. And the divergence of that vector field is zero precisely because these are maximal slices. So this unit time-like vector is a conserved current, and its flux is a flux of volume. And you can think of it as a gate current in the bulk. And it's interesting to look at how it flows and how it accounts for the growth of volume here. I'll just draw one picture of that and then stop to show you where the volume is flowing here. So here I'm drawing the case of a black hole that forms from collapse. It has some final slice in here, let's say, that looks like that. And I'll just draw two different time slices. Make sure I get this roughly right. Okay. So if I want to know that since it's a conserved current, the difference in the volume of this slice and this slice is just going to be accounted for by the flux of this gate current across the horizon. That flow vector field looks something like this over here. So there's some change of volume there, delta V, which is equal to the flux of this unit time-like vector across the horizon there. And if we didn't make the horizon the cutoff surface, but suppose we had picked, as is usually done, some surface out here at a very large radius where nothing is happening, then what we would have found is that all the flux of current across here, so there's no change, because this is just a stationary space-time out here between, what am I saying here? There's no change in the flux through here, but this flux is accounted for by flux in from a greater radius to the left. So basically what I'm saying is that complexity flows from the ultraviolet in the field theory to picture of how CFT states thermalize in the perhaps opposite way from what you would expect. Thermalization proceeds from UV to IR in a strongly coupled CFT. I say that only because there's an interesting paper by Vijay Balasubramanian plus 9 co-authors from 2011 where they studied holographic thermalization and found that, in fact, it proceeds from UV to IR. And so the same thing seems to be true for this complexity. But I think the real physical interpretation we should have of this is the following. Wherever you put this cutoff, it's like saying anything at shorter scales, that's just a vacuum. I don't have to pay the price of constructing it. That's my reference state. But I'm only going to count the complexity associated with building up everything besides the vacuum, starting at that length scale and going longer. And really, but nothing was happening until you get down to the thermal scale. So if you move that cutoff scale, it's just not going to change the rate of change of the complexity, although of course it'll change the absolute value because you're asking yourself to construct the vacuum between this cutoff scale and this cutoff scale from some random reference state. Okay, and finally, I think I could just say that I could get this formula for the complexity by looking at what is this volume? Roughly speaking, it should go like, so this section of the final slice or the surface, this section of the surface, basically it's like a cylinder, its cross-section is a sphere, and it has some length. The spherical cross-section is basically got an area equal to the horizon area. It's the same order, no matter which black hole we take, and no matter as we go late in time. So I would say that this delta V goes like the area of the final slice, which is the same as the area of the horizon, self-put area of the horizon, times this length, delta L. Now, what is that length? Well, the metric tells us what that length is. So this is basically on the final slice. It's an orbit of the killing vector. So it's the norm of the killing vector times this amount of killing time. So the length here should be the norm of the killing vector. I'll call that alpha, the lapse function, at the final slice, times delta t, the change of the killing time. But now the norm of the killing vector, well, that depends on how far you are away from the horizon. The norm is 0 here, and then it has some gradient. And by Taylor expansion, we can estimate the norm as the surface gravity. This is how surface gravity is defined. It's the rate of change of the norm of the killing vector times the proper time from the horizon to the final slice, or to whatever slice I'm on. But I just said before that time is tau f. So this should go like kappa tau f. And if you look at this and say, oh, but the area is basically the entropy of the black hole. So basically this delta V becomes the entropy of the black hole times delta L, but delta L is kappa tau f delta t. Kappa is the temperature of the black hole times tau f times delta t. So if I want to find the rate of change of, if I want to find ST, which Lenny argued should be the rate of change of complexity, I should divide the volume change by this tau f. So this is a picture of why it is that this time is the relevant time to divide the volume by, given the assumption that what you're trying to come up with is S times T. So we don't have a independent derivation of except to match to the ST expectation. But we're not just matching formulas, it's at least got a rationale generically. I better just stop there. You want to take the mic? Oh, you can, sure. Good, thanks. So, this should show you even people that work here don't know how to make this work. There we go. Okay, so what I just want to do, I guess I have 5 minutes, so I'm going to keep this super short. But I should say that just like Ted, I haven't been working on complexity for very long. We kind of stumbled upon it by accident in some work that I did with Aitor Lefkovich and Gabor Zorzi. But one thing that sort of bothered me from the get-go on complexity is that if you cannot tell me what complexity is in the field theory, then what are we doing in the first place? So that's why I very much like this recent work that Rob talked about trying to define complexity in quantum field theory. And so here's a very gross sketch of a field theory space. And I'm going to call this axis N. And this axis will be the coupling axis, like the total coupling. And so I think what we kind of understand right now is this corner here. Free field theory, one free boson or one free fermion. Maybe you can turn on perturbative couplings a little bit and talk about a few fields. But of course what we would really like is one definition that works for everything. And I don't know how to do that, but what I want to do in the next 2 minutes is give you a definition that works in the opposite corner. This is where you have a large N theory that's strongly coupled. And so to do that, I need to introduce a set of a space of states in these types of theories, which are the following. There are states that you create by doing the Euclidean path integral with some sources turned on. And there could be sources for multiple operators, and the operators that I'm going to allow you to turn on are the single trace operators. Okay, and then the wave function for such states, I'm going to call, sorry, this is not the total coupling, these are different sources. We call this G or something. Then the wave function is just given by doing the path integral with boundary conditions with these sources turned on. So I don't have time to get into this, but we've been gathering evidence that these states are the CFT states dual to semi-classical geometries. Now once you have these states, what you can do is define a metric on this space of states, which is just given basically by the pullback of the Fubini study metric onto this space of states. Okay, so the Fubini study metric is the natural metric on the Hilbert space, and you just pull it back to these lambda states, and you get some metric. And the formula for that metric, if you want, GAB, is just the following. You take, I didn't say it, but obviously the Bragg states are just given by the same path integral, but where you conjugate the sources. And so then you do the following. You do this sort of symmetric variation. Oops. So this acts on just the log of the partition function. And so this is the expression for the pullback of the Fubini study metric onto the space of states. Now once you have a metric on the space of states, you can ask, what are distances on the space of states, and you can try to write down a definition for complexity, which is a path through the space of states. And you need to introduce some cost functional that you're going to extremize over. And we don't really know right now what the right cost functional is here. There's several natural ones that you could write down. The first one is just saying, it should be just the geodesic distance. This is a nice one. It's parametrization invariant. There's some problems with this because if you have two uncoupled CFTs, you expect the complexity to be additive. It shouldn't matter how you couple the two CFTs are uncoupled, so the complexity should just add, and this will not happen here. So we thought it was slightly more natural to do the kinetic energy, which is just the following expression. And so this has the problem that it's not reparametrization invariant, so in some sense you'll have to specify how you're running the circuit here. But you can just take this definition and run with it and see what you get. And so we worked out a few examples, like Quadrato's geometry is close to the vacuum, or some sort of mini superspace thermal field bubble, and we could get nice qualitative agreement with what you expect from the bulk. But okay, so there's still a lot to explore, but what I just wanted to write down is some type of field theory definition of what complexity could be. Yeah, I hope I did 5 minutes, not more. You guys, what we do? We should, I guess, answer any questions. 10 minutes for discussion, but please use the microphone. So, since Alex has spoke, I'm just wondering what, in one of the sets of geometries you could consider making this way as black hole states. So, which definition of the length in this, what function of the Fubini study length, or whatever, is the right, gives you what Lenny's expectation for the rate of change of complexity? Oh, okay. So, yeah. Well, it depends if you have in mind a black hole formed by collapse, or you're happy with a two-sided black hole? I guess at this point, either one. Either one. Okay, so the two-sided black hole you also get in similar ways by doing the path integral over, this time not a hemisphere, but a cylinder with sources turned on. And you can play the same game and do all of this. And for us, the natural scale, sort of the only scale that you have in some sense to put for how the time is running is the temperature. So I don't know how that would, this was for planar black holes, so in some sense there's no small and big black holes. So did you check it on small and big ones? We could in principle. We haven't. And do you know that it's not just the length in the Fubini study metric in that case also? Would that be equivalent in that case, or do you have to take this? You have to specify this according to some sort of additional state dependence. So you can show that the length function doesn't work. That's really what I meant. Yes, yeah. Or even here, even in the planar black hole,
principle, you can show that this does not work.
Okay.
You get a growth that is faster than what you expect from the bulk, and so this cannot possibly be the right.
This means the square root.
The square root cannot possibly be the right thing.
Thank you.
What part of your definition depends on having strong coupling?
Okay, so large N is obvious because I talked about single trace operators. I think it would be interesting to try to move a little bit here. Our whole picture relies on the fact that basically there's a nice phase space of the gravitational solutions, and you can map that phase space to the sources that you turn on. And once you start adding this, you need to start worrying about many more fields in some sense. And so in principle, I don't think there's a sort of an obstruction in principle to trying to do this, but it's much more complicated. And so there's many more fields that you need to take care of, and so you could even worry a little bit about just doing higher derivative corrections if you wanted to explore this a little bit. But also we don't know what's supposed to happen in the bulk, right?
So your definition uses the bulk?
No, our definition is a CFT definition, but the reason we believe it is because, in some sense, we know that there's an Einstein gravity dual. We know that the phase space is under control. You just specify the metric on some slides and maybe some scalar fields and you're good to go. Certainly in this corner here, we would have a higher spin theory, for example. Then it seems much worse because you have an infinite Howard massless field and you need to get them all under control. But okay, one could try to work perturbatively around here.
Could I interpret your choice to restrict to single trace insertions as a choice of basis for what you're calling simple gate operations?
Well, the first thing that I didn't have time to say, I guess, is that these are not unitaries. We're building states with a Euclidean path integral, so this is not, there's no, I mean, they're Euclidean unitaries or whatever you want to call them, but they're not unitaries in the sense that Rob talked about. So it's a little bit, the construction is a little bit different. It's more closely related in some sense to the other picture that Rob talked about where you're trying to optimize Euclidean path integrals by Tadashi and other people. It's also different from that because in some sense in that story you're trying to optimize a norm. In some sense the path integral is some overall norm of the state that you're trying to optimize, and I'm not exactly sure what that means. Here, because we use the Fukudi study metric, we're norm independent. But it lies somewhere in between, if you want, the path integral optimization story and the unitary story.
So I guess I was just wondering, is there a place for doing deformations of sources that are, say, like double trace or multi-trace?
Wait a few months, a few weeks, I don't know. So I didn't say this, but you should think about these as coherent states in the Born gravity path integral, and double trace operators would correspond to squeeze states, and those probably also make sense, and then triple trace and higher moves you out of that sort of Pascal space, I think.
If there are more questions, I have one. So this is for all the complexity folks, and it elaborates on a question I was just asking Rob. So there's a similar set of slices there, which have this linear growth with time, basically. But once we've gotten past a time of order r cubed, which is the half-life or the evaporation time of the black hole, I think one of the messages of unitarity and the need for unitarity is that we shouldn't really trust the description of the geometry in terms of those slices any longer at that point. So I think in this general story, that's when things are getting interesting in terms of trying to make these identifications with complexity. And you're saying I have this geometrical quantity which I am supposed to be identifying with this field theory quantity, say, on the boundary, but really on the geometrical side, it's not clear that I should trust that as being some sensible thing.
You mean on the geometrical side?
Yeah.
You mean the entire space-time geometry?
Yeah, well, or at least the geometry inside the black hole. I'm trying to learn things about quantum black holes, but by the time I get this linear, by the time I get the interesting growth in the geometry in the classical black hole or semi-classical black hole, I can't really trust that picture any longer. So that's kind of a puzzle about, more deeply what the thinking and motivation is. And I'd just like to put that out there to see what you think.
But so what if I say the following words? I don't know how to say it for the collapse story and the evaporation, but if I take the eternal black hole, I could compute a two-point function on one side, and I know that there's a time at which I can't trust the geometry anymore. Right? And that time is like exponential in entropy.
Yeah, I think, well, again, a black hole in thermal equilibrium is in some respects, just like a collapsing black hole, but it's in a bath. And so, you might ask, why could I get away with trusting the internal description, to such incredibly long timescales when I can't trust it if the black hole is just, evaporating? Yeah, so it seems like it's worth thinking more deeply about that, but I don't know if there are further thoughts here.
The only thing that comes to mind is you might think about, what are the values of the complexity, in this regime where you think that the internal space-time is breaking down. And I suspect that it's far, far less than, Lenny's E to the S.
Yeah, sure.
And so something, but it's saying there's something then interesting happening. Like, if we can follow through and we really think this is complexity, it's saying something really interesting is happening at that or at that time scale in this circuit picture. But that's just I don't know what else to say.
Well, there were 3 words on the blackboard. Were they for discussion or were...
Sure.
I
can't read from over here.
You can put them on the lower board.
Yeah, maybe can I...
Well, the singularity, yeah.
It's actually in tune with what Steve was saying. This is just an extreme version. What you said before, in this case, you would say, okay, maybe this doesn't happen.
Well, I was going to say something else, which was that, if you go into the guts of the complexity equals action calculation, having a contribution from the singularity or the region very close to the singularity is essential to getting that answer, dc dt equals 2m. So that's annoying because, what's really happening at the singularity, and all I'm saying is that it's annoying. In some sense, complexity equals action probes too close to the singularity because you go right up to the singularity. In contrast, as Ted was saying, complexity equals volume doesn't probe close enough because it gets hung up. Okay, it's not a problem, it's a feature. But But well, you might ask, if interesting, if there's an interesting episode of Star Wars happening here, will we ever see that in the complexity? And yeah, no. So it's well, it's sitting there. It's not on the screen. There's lots to explore. That was my message. There are other issues that you can talk about for the singularity. If you think about higher curvature theories, we don't really understand. Like people have studied, say, Gauss Bonnet, just because it's something you can study, and there are issues with. Taking the limit where you turn off the higher curvature coupling, you don't get back to the answer that you got in Einstein gravity. But it's because of the sensitivity to the singularity. So there are issues there. I don't have any terribly insightful answers. I keep going?
So I actually think that the timescale, the relevant timescale is not into this. In this case, it's actually, well, depending on how you define it, it is either S or square root of S. And so if you could find that timescale in your calculation, it would be instructive.
Yeah, I'm not sure that you would find that timescale as a unique timescale, but it would certainly say something. What I was doing was turning around and saying that our intuition about, anybody's intuition about the growth off to, the saturation and exponential times, that there's somehow shortcuts or something interesting is happening at a much earlier time scale, which I think is interesting because, this one is,
About the scale, basically just amplifying the comments at the very end of your presentation.
Yeah, so I didn't really get to talk about that, but in defining the action, there are issues related to, I'm just repeating things for the rest of the audience, that I have to introduce boundary terms. In particular, I have to introduce boundary terms on the null surfaces of the Wheeler-DeWitt patch. Those depend on having a normal vector. The norm of the normal vector isn't fixed. And so you ultimately, because of that, you run into ambiguities in defining the value of the action. If you take the variation, there's no ambiguity in the variation of the action, but assigning a value to the action is ambiguous. Ultimately, there's a thing that we call the boundary counterterm, or it's something that ensures the reparametrization invariance of the null boundaries. In our paper, it got shuffled off to an appendix because we'd been working on the paper so long we were tired and just wanted to get rid of it. But it turned out it was really Simon Ross, I think, who was the first one to point out that maybe it's important to include that particular term. And we showed later on in the vacuum metric, which you talked about, that if I want to reproduce the switchback effect properly, I really need to include that term. Otherwise, you get nonsense answers, or you get answers that would not be consistent with the switchback effect. And so it seems when you define the Wheeler-DeWitt action, you better include that particular contribution. There's still a scale involved there, in that it involves an integral of something like theta. So this is the expansion, but that's a dimensional thing. It's theta log theta, and so there's a scale that you introduce there. So the ambiguities about the norm of the null vector disappear, but there's still an ambiguity here that comes into the game.
Were you saying that all these ambiguities in your microscopic calculation?
I was probably saying something like that, but it was an aspiration, not a statement of fact. I mean, there are other calculations that we're doing now which seem to, that picture seems to be falling apart a little bit, so it's not clear anymore. But at the time, it was a real surprise to me that, we had done this calculation in holography, and I found something that was kind of disturbing, or at the time it was disturbing to me, kind of made me start to doubt. And then when we did the simplest field theory calculation, very similar ambiguities popped up. And so it seemed that it was just one of these things that, complexity is a new kind of a beast, and we just have to understand what its properties are and come to grips with it. In the same way that, I think there was a similar story when entanglement entropy came into the game in holography. There were new kinds of properties. The UV divergences that you mentioned for complexity that were perplexing to you, I actively ignored entanglement entropy for 4 years because of those same divergences, and I thought this is all nonsense. And so the lesson I learned is, don't worry, just keep going. And I can add there that, I'm sympathetic to your perspective. What you learned in entanglement entropy was, there are problems with the entanglement entropy itself. Sometimes there are universal terms that you can identify in a unique way, but another thing you can do is you can think about differences of entanglement entropies. Sometime somebody was talking about the mutual information. The way we understand that is that the difference of entanglement entropies, and one of the key features is that you eliminate those UV divergences. So in the same way, this complexity of formation that I talked about, you could compare, what you were saying, where there are all these problems, or there are these issues out here, there's a lot of stuff that you're not interested in, that's basically the same as in the vacuum. So if you subtract off the vacuum contribution, I'm going to get a finite answer, and I can think about that difference as being an interesting quantity that tells you about the robust or the interesting finite stuff in the evolution of the black hole. I focused on a calculation on a t=0 slice, but in our thermofield double paper, we did the same subtraction up here just because it's an easy way to get a finite answer that you can put on a plot.
Make sure to stop for a little break. Thanks to the three speakers. So let's come back at 10:40.
and my co-patriots here are going to give an introduction to the discussion, and that is going to be a very introductory, introduction to the introduction, in which I'll pull you a little bit out of the theme of the conference and just talk about quantum field theory with not much to do with gravity for a while, and Andrea and Jeffrey will pull you back to where you've been the last while. So I'd like to talk a little bit about some work that we did on infrared divergences, and this is really related to the